Hey folks, I want to give a couple more examples of maps between groups that are homomorphisms or not. So let's begin with one on the dihedral group. So we're going to map the dihedral group to the integers mod 2. What is the dihedral group? So take a regular polygon. Like here I have a regular hexagon. The dihedral group D6 would be the group that is all the symmetries of this hexagon. So it's going to have 12 elements. It's going to have 6 rotations, and then it's going to have 6 flips. The flips are across these 6 possible axes. All right. So how am I going to define this homomorphism? I'm going to send a symmetry sigma to 0 if sigma is a rotation. And I'm going to send this symmetry sigma to 1 if it is a flip. All right. So the fact that this is a homomorphism relates to inside this group Dn of the symmetries of an n-gon, we have this pattern. This pattern looks as follows. Whenever you take 2 rotations, no matter what they are, if you combine them, you get a rotation. And if you combine a rotation with a flip, you necessarily get a flip. But if you combine a flip with a flip, you get a rotation back. Any 2 flips, if you do them in succession, you get a rotation out. So in this much larger group, we're finding this pattern that looks like the structure of Z mod 2Z. And it's being exhibited by this homomorphism. So we're sort of collapsing down a lot of information from this large group, maybe the symmetries of the hexagon, 12 different symmetries. We're collapsing down just to a group of size 2. But we're encoding this pattern that, we're sort of simplifying things and just observing that any 2 rotations in this large group combine to a rotation. And a rotation combined with a flip is a flip, whereas 2 flips give you a rotation. 2 of the same flips gives you the identity. But if I do 1 flip and then another flip, that's always a rotation. So my cell phone's not a square, but if I do a flip and then a different flip, that's just the same as, okay, let me try this again. If I do a flip and then a different flip, that's just the same as a rotation. All right, I want to do a non-example. Let's look at this map from the reals under addition to the reals under addition. Let's map a real number x to x squared. This is not a homomorphism. To be a homomorphism, I would always need that phi of a plus b is equal to phi of a plus phi of b. Okay, but these are not always going to be the same. Phi of a plus b is a plus b squared, which is a squared plus 2ab plus b squared. Whereas phi of a plus phi of b is just a squared plus b squared. So as long as neither a nor b is 0, these are going to be different. So if I want to get more concrete, for example, maybe let's just take A and B to each be 1. A and B to each be 1. So then phi of A plus B is phi of 1 plus 1, or phi of 2, which is 2 squared, which is 4. That is not equal to phi of A plus phi of B, which is phi of 1 plus phi of 1, which is 1 squared plus 1 squared, or 2. All right, so phi of A plus B was 4. Phi of A plus phi of B was just 2. And since 4 is not equal to 2, we've found inputs verifying this is not a homomorphism. Let me change the operation a little bit, and in some sense, I will turn this into a homomorphism. So let me consider the non-zero reals. So the star means non-zero. Under multiplication. So the star means 0 is excluded. And the non-zero reals are a group under multiplication. Let's define phi in the same way. Phi of x is equal to x squared. This now is a homomorphism. Since now how do I combine A and B? I multiply them. And I want to show that that's equal to phi of A combined with phi of B. And how do I combine phi of A with phi of B? I also multiply them. All right, so phi of AB is AB squared, which is AB. But multiplication of real numbers is commutative. So this is just A squared. Well, I guess I could write it as A times B times B, since we're in the real numbers, which is a commutative group. And this is A squared, B squared, which is phi of A times phi of B. All right, I lied. I'm going to do one more example while I have you here. This is for folks who have seen linear algebra, and no worries if you haven't. Okay, so that the general linear group be the set of all 2 by 2 matrices with non-zero determinant. All right. And the matrices have entries that are real numbers. I'm going to define a homomorphism from this group of matrices to the non-zero reals under multiplication by, let's take a matrix A and let's just map it to its determinant. Okay. I said that my matrices had non-zero determinant, so that's why I avoid 0. So this is a group homomorphism. Since for all matrices A and B, maybe you've learned this property in linear algebra that the determinant of a product of matrices actually turns out to be the product of their determinants. Okay. So if this is ringing any bells from linear algebra, right? This is sort of, think on the left side, this is phi of AB, and on the right, this is phi of A combined with phi of B. So if you remember learning this property in linear algebra, right? Like if the way matrix A scales area, and if you consider the way that matrix A scales area and you consider the way in which matrix B scales area, then the way that the product matrix scales area is just by first scaling by the way matrix A scales area and then scaling by the way that matrix B scales area. So homomorphisms are a powerful language, and things that you might have seen in other classes can actually be phrased as homomorphisms of groups, which is what we have here. This is not only a set of matrices, this is a group under matrix composition, matrix multiplication. And here we have our homomorphism mapping any matrix simply to its determinant. All right, I rambled on for a bit there, but any public questions? Thank you.